Welcome back after a break, and we are very sorry that we have some delay, but technical aspect was much bigger than us. And now we are back with Volker Janz, who is expert data engineer at InnoGames, and Volker will talk for us with his presentation about real-time customer engagement in gaming using Kafka and Flink. As always, you can post your question to the Volker on a chat, so don't hesitate, don't wait until the end, just post them during the presentation. Volker, the stage is yours.
Yeah, thank you very much. And yeah, welcome to my presentation, Real-Time Customer Engagement with Kafka and Flink. And I'd like to start with a little out of the ordinary introduction to the topic, I would say. So imagine that you're driving in a car with your family on the back seat, and there's lots of traffic on the road, and you're driving concentrated the car. And now imagine that you close your eyes. And since you're sitting at home, it's fine. Just do it. Close your eyes. Nobody will know. And think about, how do you feel about that? You may open up your eyes again. And my question is, would you do that? Well, the answer is most certainly no, because you would put the lives of your loved ones into danger, and that is something you would not do. What would you do instead? Well, instead you would check the data around you while it happens to safely drive the car. So in fact, what you do is stream processing. You check the data while it happens instead of waiting until the day passes and then you open up your eyes. No, instead you react to the data while it happens. And this brings me to the motivation of this talk, which is, and that is the thing you should take out of this talk, life doesn't happen in batches. That is a quote from Alan Friedman and Ted Dunning. I recommend reading this article linked below. And with that, I would like to introduce myself. So my name is Volker. I'm an expert data engineer working at InnoGames in the beautiful city of Hamburg, Germany. And I have 2 kids. You can see them there in the background. So this was our first real family vacation this year. I also like to do photography, and in the background you might have seen here, I think, yes. I like retro games and consoles, so if I have any time left, I spend playing old stuff, basically. I also have LinkedIn if you like to connect. So I'm working at InnoGames in the gaming industry, and we have lots of games out there in the field of simulation, strategy, and RPGs. And what do all these games have in common? Well, they produce data. They produce streams of data. And if we look at streams of data, they are basically everywhere. So everything you see, GPS data, web interaction, game interaction, sensor data, everything is naturally kind of a stream of data. And if we talk about stream processing, it means to process data in motion while it happens. So a streaming application usually looks like this. You have a source, you have an operator, and you have a data sink where you store the data. And if we look at the gaming industry, what kind of data streams do we have there? Well, our main data source, our main data stream are the interactions with the game. So if you play the game, the data that is tracked, this is the main data stream. So by example, if you play this game and you build a building, you get a build event. If you do a quest, you get a quest event. If you fight another player or the computer, you get a fight event. Or if you invite a friend or colleague, you get an invite event. And all this is tracked as JSON for us. And we track this using our data infrastructure, which I would like to show you next. Be aware, this is quite a heavy slide. But yeah, I wanted to share it with you because this is built on a lot of history, because I'm working at InnoGames for 13 years, and this architecture has evolved over the last, I would say, 11 years or so. So it's quite solid and has changed a lot over the years. But let's go through it briefly. I hope you can see the red laser pointer I have here. So on the left-hand side, we have the event client, which is a small component written in the Go language running on the game backend servers. This is transmitting the game interaction events to our event gateway, which is the entry point for all the data. Here we are applying some JSON schema validation to see if the events are valid or if they're invalid. We then store everything in the event bus where data exists as a stream of data. And this is also where we do stream processing, obviously. In the batch world, we use everything that the Hadoop ecosystem has to offer. So we use Hive to process the data with the test execution engine. We use R, Spark, Python, you name it, we have it basically. We use Airflow to orchestrate everything. And we also recently added Google Cloud in to have like a hybrid cloud infrastructure for the batch processing part. We also have a BI stack based on SQL Server, and we use Power BI to visualize some of the data. However, if we talk about stream processing, only the left-hand side is interesting for us, because stream processing for us means we want to react to the events when they happen, basically. And the key technologies here for us are Kafka and Flink. So I would like to briefly talk about those before I show you like a practical example, what to do with this. So let's have a look at Kafka. Kafka is a distributed event streaming platform. What does it mean? What can it offer for us? First of all, you can write and read streams of events, which also means it needs to be able to store these streams of events. Recently is not correct, but in the beginning, Kafka was just a message broker, and then they added the capability to also process streams of events. So you can also process the data right in Kafka. Now, the way we use it looks like this. We store our data in two topics. So about topics, your Kafka cluster consists of so-called brokers, and your data is organized into topics. We have two topics, events valid and events invalid. So here you can already see one important concept, which is to track everything, no matter if it's valid data or invalid data. If you zoom into one of these topics, the topics are split into so-called partitions. You can configure the number of partitions on your own. I will come to that in a minute. So the topics basically are buckets which are located across the different Kafka servers or brokers that you have. And if you zoom into a partition, you will have a number of segments. A segment is basically a file stored on the broker's disk. And this is important to know because the broker will keep up file handles for each and every segment on the disk. So it's also important to know how to configure and influence these. So I added some configuration variables here, but you can check them out later when you get the slides. So we now want to write and read from Kafka. Let's have a look how this works. Basically, you have producers to write data to Kafka and consumers to read data from Kafka. The producer produces messages which always have a key, a value, and a timestamp. For us, the key is the player ID, so something to identify the user. The value is the JSON event, so the game interaction event. Here we have a build event, so a player built a building in the game basically, and in the data you can see some details like what kind of building it was. We have 1.7 billion events per day. This is the amount of data we deal with basically. And our events valid topic has 32 partitions. Now you might ask, is that a good number or not? Well, for our use case, yes, it's enough, but I recommend to actually configure more partitions because adding partitions later is a little bit of pain, I would say. It works, but it's very stressful. And actually, Confluent recommends up to 4,000 partitions per broker and 200,000 partitions in total per cluster. You should be aware that if you have more partitions, your end-to-end latency will increase, you have more memory usage. Also, Zookeeper will have more work to do basically for the leader election. But 32 is a good number, but I would recommend a little bit more for this amount of data actually. Now, if we read data from Kafka, we have so-called consumer groups. You can imagine that each consumer group is one use case. So one of your applications is usually connected to one consumer group. Within a group, you can have any number of consumers, and Kafka will automatically split the data between the consumer instances equally. This is a pretty cool feature. However, if you have more consumers than you have partitions, like in this example with 33 consumers, that you will have one very unhappy consumer because it gets no data at all. So bear in mind that the number of partitions also controls the way how you can parallelize the processing of data later. Keep that in mind. Let's switch to Flink. Flink not only has the best logo of all open source projects, this nice squirrel you can see over there, but also it's a framework and distributed process engine for stateful computations on unbounded and bounded data streams. What does that mean? Well, in Flink, you have three main components: data sources, transformations, and data sinks. And you have APIs how to define those. And you work with unbounded streams, which have a defined start but no defined end. And bounded streams, they have a defined start and a defined end, and this is also what we know as batch processing. So you can see already one important concept. Flink tries to combine everything, and you have a unified way to process batch and streaming data. Talking about APIs, we have 3 different APIs. The high-level analytics API is the SQL or table API. This is pretty cool because you can use Flink SQL, which is almost ANSI SQL, to explain what you want to do in your stream processing application. You can also use Python, Java, and Scala. And the data stream API is the most commonly used, I would say. So you have lots of freedom, but it's still rather easy to describe your streaming application. You can use it with Python, so PyFlink, or Java or Scala. And if you need full control over everything, you have the process functions, which are then written in Java or Scala. I also tried Kotlin, so you can in theory use other JVM languages, and it works, but it's not officially supported at least. So let's have a look at an example. Imagine you have a website and users click around on your website, and now you want to sessionize the click stream and count the number of clicks per session. So using the data stream API, it would look like this. You have your clicks, and then you project each click to a tuple of 2, which contains the user ID and the number 1 for counting. Then you key your stream by the user ID. This will split your stream basically into partitions by the user ID, which also has the effect that the same worker instances always process the same key. So it's also a method to preserve order in your stream. So then we define the session window, which is a pretty cool feature because it looks for gaps in your event stream, and we look for a gap of 30 minutes. If we found one, then we have the sessions. And then we reduce everything, count the number of clicks per session, and that's basically it. Now, that looks okay, I would say, but if you look at the SQL example, it looks much more intuitive and easy because you can simply use an aggregation function and group by this session window. That's basically it. However, streaming SQL is a little bit different from batch SQL. Because streaming queries, they have to wait for data to be streamed. That also means they never really finish. They create continuous results over time. And the underlying concept here are so-called dynamic tables and continuous queries. If you want to know more about it, I can recommend this practical talk. It's available on YouTube. It's called Real-Time Analytics that Controls 50% of Mobile Network in Poland. And I think it's quite interesting because it's a practical example how to apply Flink SQL. Anyways, let's continue. So let us talk about state. If we have a stream of data and we look at one event at a time, this is called stateless stream processing. So this could be like a temperature sensor, and we send an alert whenever the temperature is higher than a threshold. However, in most cases, we want to remember information across multiple events, and this is called stateful stream processing. And the good news is Kafka fully supports that. Flink, sorry, Kafka as well, but we are at Flink. So Flink fully supports this. And the 2 types of states we have in Flink are keyed state and operator state. So keyed state is associated with a specific key in the stream. This could be storing the session duration and total session count in a stream keyed by user, for example. The operator state is only bound to one parallel instance of the operator, no matter what key it is. And this could be maintaining the offset for a Kafka per partition. Usually you do not use operator state. These are quite special, and in your day-to-day applications, you would use the keyed state. If you look at it at a picture, well, that's basically it. So you read different keys from Kafka, A, B, C, D. The offset is stored as an operator state. And then if you key the stream by this letter here, then it could be that this map instance, for example, only stores the aggregation for key A and B. Okay, so there's one more concept I wanted to add here, because this is something that people often mix up, unfortunately. It's checkpoints and save points. So checkpoints are based on the Chandy-Lamport algorithm, and they decouple checkpointing from processing. And it's a concept where they mark a point in time in the input stream along with the state for each operator. And it's a mechanism to recover from failures. It's not meant to be resumed when the application was explicitly cancelled. So it's really a failover mechanism. However, save points, these you can trigger manually, and then you can start your application with a save point to resume from a certain state. So this is a huge difference. Keep that in mind. Now, to get back your attention, I prepared this fancy animation to now start with the use case I brought for you today, which is customer engagement. So let's have a look. And I think the easiest way to explain it to you is by watching a video. So let's see if that works. Okay, this is me playing one of the games that we produced. It's called Rise of Cultures. You can see I'm fighting these troops and I lost the fight. I'm very frustrated. I think about stop playing the game. The system in the background detects this interaction and reacts on that. And as soon as I reach my city, I get this offer in real time, tailored to my needs. So now I'm happy because I can get exactly what I need to win the fight and to continue playing the game. Now this is of course an artificial example just to show you the idea behind it. Okay, how does it work? We start with a bird's eye perspective and then we zoom in step by step so that you understand exactly how it works. Okay, we start with the fight event. So I lost the fight, which generated a fight event. So event name fight. In the data, you can see that the result was loss because I lost the fight. And on the other hand, what we have are so-called CRM campaigns. These have an ID, they can be enabled, they are related to a game, they listen to a specific event, in this case the fight event, they have a start and end date, and then there's a magic ingredient, which is the filter function. The filter function is a piece of JavaScript which is applied to this input event, and it returns either true or false. And with that, we can control whether the offer should be triggered or not. And in this case, we take the event as an input and we just check what was the result. If the result was loss, so if I lost the fight, I get the offer. We do this, by the way, with the Nashorn engine in Java, which is deprecated, yes, but there's a standalone version from OpenJDK available on Maven Central, and you can use it with Java 15 and beyond, and that works pretty well for us. So all this goes into Flink. Flink evaluates everything, and then if everything is met, then the special offer is triggered for the player. Okay, let's zoom in one more level. So the game writes data to the event's valid topic in Kafka, like the fight loss event. This goes into Flink. Flink is doing some magic, and I will let you know what the magic is in a minute. And then Flink will write back to Kafka into another topic. So you can see we really use Kafka here as a message broker. And this topic, it's called CRM trigger, is read by the game. And if there's an event, they will trigger the offer, basically. So customer engagement for us means reacting on specific events with specific attributes to trigger an offer for the player. And this is called a campaign. Now you might ask, hey, how can we configure these rules at runtime? Because you don't want to redeploy the application every time. And the cool thing is that stream processing has an answer for that, which is the so-called broadcast state pattern. And the idea here is that you have another Kafka topic which you use to distribute the configuration. So we call it CRM campaigns. It's low frequency Kafka topic. And whenever there's a new campaign definition written to this topic, it gets broadcasted to all the functions in Flink. They store it in their state, and that way you can configure the application at runtime. Now, I also want to show you some code, how to do that. So it's rather straightforward if you know how it goes. I mean, the documentation could use more examples, so I try to give you one more example right here. So you describe the state, you tell Flink what kind of data types you want to store in the state. Then you create a broadcast stream from a Kafka source. So we're reading this Kafka topic containing the campaigns. What we do here is we have a map function that projects this JSON string to a plain old Java object, to a POJO, which is called campaign. And then with .broadcast, we tell Flink that this is a broadcast stream. We then connect everything. So we have our main event stream and we connect it to the campaign stream. And the next process function here, which is doing all the magic, the evaluate filter function, is a special broadcast function because it gets the event stream, but also the broadcast stream. So it has to extend the broadcast process function and has to implement the process broadcast element function here. And here you have to tell Flink how to react whenever there's a new broadcast element broadcasted to the function. So in our case, whenever we get a new campaign, we store it in the state, and that's basically it. Okay, now we have all the details, all the ingredients. Now we can zoom into the highest detail level, kind of. So we have the game. The game is writing to events valid in Kafka. Then there's an event like fight loss, for instance. These JSON events are read by Kafka, and then we have the first map function, which is projecting the JSON string to a plain old Java object. We call it tracking event. These go into the evaluate filter process function. This function is aware of all the campaigns. It will iterate over each and every campaign, and it will see if there's a match between the campaign and the tracking event. To do that, it needs to be aware of the campaign. So we have the broadcast stream right here, which reads from a different topic, and the campaigns are broadcasted to the function, which stores it in its state. If there is a match between a tracking event and a campaign, this information is sent to the trigger campaign sync, which will write the information to another topic called CRM trigger. This is read by the game, and whenever there's a trigger, it shows the offer to the player. So I called this real-time CRM. So I wanted to also give you some numbers about that. The difference between writing to the events valid topic and the CRM trigger topic is actually less than 1 second. In fact, it's just a few milliseconds, but to be safe, I just say less than 1 second. I think it's okay. Now, I have a little surprise for you. I know Christmas is coming up, so I have a little Christmas present for you, which is that I created an open source version of this Flink application just for you. So you can check it out on GitHub, basically, and it contains the full Flink workflow you can see here. You will also get the links in the slides later. What else I prepared is I created a little demo UI also just for you, because obviously I can't open source our game code, then I would get into serious trouble. So I created like a demo UI which can interact with the Flink job. Yes. Then one more thing, at InnoGames we brought this to the next level kind of. So we extended all this, and I want to give you an idea of what we did. What we did was to add these two things over there. So first, we also used each and every event to update a so-called player profile in a key value store. So for instance, if you buy diamonds in a game, we update in real time the information how many diamonds you bought. And then later, attached to the campaign, we also have a so-called segment, which defines which groups of players are eligible for the offer. So what we can do is we can say, yes, you have to lose the fight, but also you have to buy at least 100 diamonds. You also have to buy 100 diamonds in the past to be eligible for the offer, kind of. And this gives us more control about the groups of players that receive this offer. This was quite a lot, I know. So to get back your attention, I have a short demo for you. And I hope it works. I mean, it's a live demo on a conference, so please keep your fingers crossed. Let's see. So let's get started. First of all, you can see here that I have Docker running on my local machine. I have a Kafka Docker box and also Zookeeper. So 2 containers, which is the minimum I need to have Kafka running. I can also show you how that looks like. So I use a tool called kcut to interact with Kafka. With -b, I can specify the broker. So I'm connecting to localhost, -L will list the topics. And I apply a little grep here to not get too much output. And if I do that, you can see we have these 3 topics I showed you in the slides. Now, let's switch to the first project. Like I said, these are open source on GitHub, so you can check them out later. This is my Flink application. And you can see already I'm doing lots of configuration stuff. I added comments for you so that you know what I'm doing here. And you can see down here, I'm creating my broadcast stream. So this is what I showed you before. And here I'm creating my main event stream. And here I connect everything. So I have my main event stream connected to the broadcast stream, connected to the evaluate filter function. If we go into the evaluate filter, you can see it has 2 main functions. One is the description, how it should deal with regular events. You can see we iterate over all campaigns and see if we have a match. And whenever we get a broadcast element, so update of the configuration, we just store it in the state. And the sync, so the last step in the stream, is just sending the information to Kafka. Let's start it. I can show you a little trick, which is pretty cool, because if you create a local Flink application and you create this environment, you can use create a local environment with web UI, and then you even get the Flink web UI on your local machine. Let me show it to you. If I go to localhost 8081, I get the Flink UI, and you can see the running pipeline over here. So I have my broadcast stream over here and the main event stream over there. Here you also see one concept of Flink, which is that it groups together things in your stream if it makes sense to so-called task groups. So here it combined the evaluate filter and the sync into one single task group. Okay, now interacting with the system, we could use the CLI for that, but that would be boring, to be honest. So I created another project just for you, which is a demo UI. And this is a simple Spring Boot application, so I will not go into details here, but let me start it for you. Keep in mind, I'm not a front-end developer, so it's not super pretty, but I hope it works. Let's see. It's running on the different ports like that. This is how it looks like. And it's just so that you get the idea of what the system does. On the left-hand side, you can imagine this is how the CRM manager configures the campaigns. So we could have a campaign listening to fight events, and the filter function checks if the result of the fight was loss. If I send this to Kafka, the system is configured, basically. This went through the broadcast stream now. Okay, now we are playing the game and we are losing the fight. So we get a fight event with the result loss. And this should now trigger the campaign. And let's see what happens. Hopefully it works. Keep your fingers crossed. Boom. Okay, it worked. That's good. And you can see already here on the right-hand side, this was now triggered by Flink, so it wrote the information to Kafka that we should show something to the player, and then this could be like a simple pop-up in the game or something like that. If I generate this event again, and I change the result to win because I learned from my mistakes, I'm now winning the fight, I send it to Kafka, nothing happens because the campaign explicitly filters for loss events. If I now change the campaign configuration, so I change the filter function to listen to win events. So I change this filter over there and I send it to Kafka. The state in Flink will be overwritten with this updated campaign, which means if I now send this event again with result win, it should trigger the offer now. Let's see if it works. Yes, it did. And you see it was immediately, it was right there. So this way you can configure this the system at runtime and interact with it. Yeah, like I said, both of this is open source, so feel free to check it out. Now let's go back to the slides. I have something else for you, which is a brief outlook to the future. So future era. Now this is already pretty cool, but what can you do with it further if you want to develop it to the next level? These are just ideas, so this is something we didn't do yet, but which is something we might do in the future. The idea could be that you add a little bit of machine learning to the whole thing. So first of all, the idea is that you have a centralized feature store. One feature store could be Hopsworks, which is an open source feature store for machine learning features, but it also has a model registry and can do model serving for you. Now, the idea is that we learn in batch, so we train the models in batch, maybe on our Hadoop cluster, maybe somewhere else in the cloud, wherever. We then get a serialized version of the model, could be something like JPMML or so, and we broadcast these models to the functions, which store them in their state. And then we use this update function in Flink to update the feature store in real time. And then later in the segment function, we get the up-to-date feature vector for the current player, and then we predict in streaming. So learn in batch and predict in real time in streaming. And this is pretty cool if you think about it. Imagine you have a campaign which works like it's listening to these fight loss events, but you only get the offer if the model predicts that it's very likely for you to churn, so to leave the game and stop playing. And this could be a very powerful way to have very targeted customer engagement. Now, why did I choose Hopsworks? Because they have a very cool integration for Flink, actually. So if you look at it, they support inserting a native Flink stream to the storage. And this is pretty cool. I mean, this is a different example with Ethereum prices, but you get the idea. You can just insert a stream of data to the feature store. And with all that, I just hope I could inspire you to work with streaming applications, because if there's one thing you take out, it is life doesn't happen in batches. It's very worth thinking about streaming applications, and streaming applications can also be much more than just having some dashboards. You can see they can even have some operational value for you. And with that, thank you very much. I hope you enjoyed the presentation. Remember to leave questions, rate the presentation, and one more slide, sorry, which are the links to GitHub, because I promised I will put them here. Feel free to check it out. Also, see you on LinkedIn. I'm quite active there. I'm happy to connect. If you have feedback, also feel free to tag me in a post. And one more thing, and then I'm done, promised. You know, I like retro games, and one thing I really liked about gaming has always been the hidden stuff inside the games, the bonus levels. And I have a bonus level for you. So if you get the slides and you continue scrolling, you will reach the bonus slides. And these have lots of learnings I discovered during implementing all this. So I added some stuff for you here. You will get more details about ice cream. Yeah, you will see what I mean with that. And you also get some details about the Flink runtime and so on and so forth. So a lot of information hidden there in the slides, but I know time is limited, so I added everything as bonus just for you. And with that, thank you again for watching, and I hope you have a wonderful conference. Thanks.
Okay, thank you very much, Volker, for your presentation. As I look on our chat, and I'm looking for a question, but only I can find congratulations for you, like the best presentation so far.
That's sweet.
And impressive presentation. So that was great. Another comment on the chat. So congratulations for a really magnificent presentation.
Thank you very much.
We will wait a minute if there will be any other questions to you. Only great presentation. So I also say it was a great presentation. And don't forget to rate Volker's presentation using QR code that was inserted in a presentation, or using stars under the video player. So we will know that it is the best one.
Thank you.
We
very
want
much.
more. So the bonus idea was also a fantastic idea to involve. So people likes it.
Good.
Okay, I don't see. And one question: do you have your own YouTube channel?
Good question. Yes, I do, but it has nothing related to data on there. But it's easy to find if you look for it. Let's put it this way: you learn something about game development. Let's see.
Okay, so I don't see any other questions. So thank you very much for your presentation. Thank you very much for your participation, and don't forget to rate this presentation. See you after the break.
Cheers. Have a good day.